Section: Introduction. In this section, we discuss the recent advancements in autoregressive models, particularly those utilizing the transformer decoder architecture, which have significantly transformed large language models. These models excel at predicting the next token and have shown remarkable performance and scalability, greatly influencing generative tasks. Building on this success, we have seen researchers investigating the use of large autoregressive models for visual generation. Notable examples include VQGAN and DALL-E, which adapt the autoregressive method by converting images into discrete tokens and generating them one after another, achieving impressive results. However, the rise of diffusion models has set new performance standards, surpassing autoregressive models. Despite this, diffusion models have limitations in scalability, while autoregressive models are better suited for large-scale applications. Additionally, the differing approaches of diffusion and autoregressive models create challenges in merging language and vision models, prompting ongoing research into autoregressive visual generation. Recent progress has shown that autoregressive models can produce generation quality that competes with or even exceeds that of diffusion models. Innovations such as next-scale prediction techniques and advanced architectures like Llama have contributed to this progress. Nonetheless, we still face challenges, particularly regarding computational efficiency due to the complexity of visual data and the high computational demands of transformers. To tackle these issues, we are exploring linear attention mechanisms as alternatives to traditional self-attention in transformers. One promising model is Mamba, a state space model designed for efficient sequence modeling with linear complexity. Mamba has excelled in language tasks and is now being applied to visual tasks, although its potential for autoregressive image generation has not yet been fully realized. To fill this gap, we introduce AIM, the first autoregressive image generation model based on the Mamba architecture. AIM uses a next token prediction approach with enhancements tailored for visual tasks, including a new adaptive layer normalization method called ADALN group. These improvements optimize performance while keeping the parameter count manageable, leveraging Mamba's efficient modeling for class-conditional image generation. On the ImageNet 1K256x256 benchmark, AIM achieves a Frechet inception distance of 2.21, outperforming existing transformer-based autoregressive models of similar sizes and showing strong competition against diffusion models. Notably, the smallest AIM model achieves a FID of 3.5 with only 148 million parameters, outperforming other models that require more than double the parameters for similar results. Additionally, AIM provides significantly faster inference speeds compared to both transformer-based autoregressive models and diffusion models. In summary, our contributions include 1. Introducing AIM, an autoregressive image generation model based on the Mamba framework, which offers high-quality and efficient class-conditional image generation. 2. Adapting the architecture for visual tasks by incorporating positional encoding and a new adaptive layer normalization method, ADALN group, to optimize performance and parameter count. 3. Developing AIM at various scales and demonstrating its state-of-the-art performance on the ImageNet 256x256 benchmark, along with fast inference speeds, highlighting AIM's efficiency and scalability. Next, we will discuss related works, starting with VQ-based autoregressive generative models. The VQ-VAE introduced a groundbreaking approach to image generation by compressing images into a latent space and quantizing them into discrete codes. These codes are then modeled with a pixel CNN, predicting the probability of each code based on previous ones in a raster scan order. This two-stage process has laid the groundwork for many subsequent models, including DALL-E, which uses transformers for autoregressive token generation, and VQGAN, which enhances image tokenization with adversarial and perceptual losses. Recent models like VAR and Llama Gen have continued this trend, showing better performance than diffusion models. This two-stage approach separates the generation process, allowing the second stage to focus on sequence modeling without biases from visual signals. This enables linear complexity autoregressive models, such as Mamba, to efficiently perform image generation without needing complex adaptations. We also explore state space models, which are designed for long sequence tasks and are closely related to RNNs. These models use hidden states to effectively capture temporal dependencies. The recently introduced Mamba model features a selective scan mechanism that employs techniques like kernel fusion and parallel scanning, addressing the computational challenges of state space models and creating a scalable network backbone for various tasks. Mamba 2 further develops this by introducing the structured state-space duality framework, showing that selective state space models function as a generalized linear attention mechanism. With their linear complexity and strong modeling capabilities, the Mamba family presents a promising alternative to transformers for long sequence modeling tasks. Section Summary. In this section, we discuss the evolution of autoregressive models, particularly in visual generation, highlighting the introduction of AIM, an autoregressive image generation model based on the Mamba architecture, which achieves state-of-the-art performance on the ImageNet benchmark while maintaining efficiency and scalability. We also explore the foundational concepts of VQ-based models and state space models, emphasizing Mamba's innovative mechanisms that enable effective long-sequence modeling with linear complexity. Section: Mamba in visual generation. In this section, we explore Mamba's applications in visual generation. Recently, we have seen initial efforts to adapt Mamba for visual signals using multidirectional scanning techniques. For example, the VIM uses a bidirectional scan, while vMamba scans input patches in 4 different directions. These methods utilize various SSM blocks to process each directional input separately and then combine the results to create 2D representations. However, these multidirectional scans add extra parameters and computational costs, which reduce Mamba's speed advantage and increase GPU memory usage, making it harder to use Mamba for visual tasks. To tackle this, Sigma introduced a zigzag scan that uses 8 scanning directions to gather 2D spatial information, distributing the scanning process across layers. Similarly, DIM alternates between 4 scan directions. In contrast, we uniquely adapt Mamba for autoregressive image generation, maximizing its ability to model long sequences and following a next prediction approach, allowing us to achieve high-quality image modeling without needing additional scanning strategies. In our method, we adopt a 2-stage approach, as previously described and illustrated in our figures. Our main goal is to advance the use of Mamba in autoregressive image generation, following the same initial stage as VQGAN and LDM. The key contribution of our work lies in the second stage. Mamba effectively manages sequence data for autoregressive tasks like language modeling. It builds on state space models that relate sequences over time using hidden states defined by certain parameters. Mamba discretizes these continuous parameters using a timescale, allowing for recurrent solutions that align with unidirectional next token predictions in autoregressive modeling. By integrating continuous and discrete dynamics with dynamic parameters, Mamba captures temporal dependencies and sequence patterns, making it suitable for both language and vision tasks. For visual generation, our model architecture is primarily based on native Mamba, with 2 significant enhancements to better handle the spatial characteristics of images and class conditional generation. First, we address positional encoding. Native Mamba does not use positional encoding because the SSM captures positional information through its recursive mechanism, which works well for text as it is inherently sequential. However, images are 2-dimensional and need to be transformed into a sequence, which can confuse the SSM when it comes to recognizing new rows. This limitation can lead to inaccuracies in generated images, such as mirror artifacts. By adding simple absolute position encoding, we have resolved these issues, allowing for more accurate and coherent image generation. Second, we implement Group Adaptive Layer Normalization, ADALN, a technique that adjusts data distributions based on conditional information. While ADALN has proven effective in various visual generation models, it can significantly increase parameter counts and GPU memory usage. A variant called ADALN single reduces parameters by computing global scale and shift parameters once and sharing them across layers. However, this can lead to performance trade-offs. To find a better balance, we propose a DALN group, which divides layers into groups that share local parameters while still allowing for layer-specific learnable parameters. This approach optimizes memory usage without greatly sacrificing performance. Our experiments suggest that setting the number of groups to 4 strikes the best balance between model parameters and performance. For more details, we refer to the experiment section. Section Summary. In this section, we explore the adaptation of Mamba for autoregressive image generation, enhancing its capabilities with positional encoding to address spatial challenges and introducing a group adaptive layer normalization, ADALN group, to optimize parameter efficiency while maintaining performance. Our approach allows Mamba to effectively model images without the computational burdens associated with traditional multidirectional scanning methods. Section: Image generation by autoregressive models. In this section, we discuss image generation using autoregressive models, which typically follow a next token prediction approach. A key difference in conditional generation is the use of extra information, like class labels or text. Our focus is solely on class conditional generation. For class conditional image generation, we start by embedding class labels and adding them to the beginning of the image token sequence. These embedded labels also undergo a transformation to create scale and shift parameters for adaptive layer normalization, ADALN. The model learns to predict the next token based on the previous ones. During training, we input tokens into the model, which then predicts the probability of the next token. We calculate the loss by comparing the model's predictions with the actual target tokens, which are the input tokens shifted by one position. Specifically, if we denote the ith token as q_i and all previous tokens as q_i, the model predicts the probability of q_i given q_i and the class embedding circa. Our goal is to minimize the negative log likelihood, where n represents the total number of tokens. This method helps the model learn to predict each token based on prior tokens and the class label. We also use classifier-free guidance to improve the quality of our generation. This involves training the model in 2 ways, conditionally with class labels and unconditionally without them. During inference, we blend the unconditional model's predictions with those from the class conditional model, controlled by a guidance scale W. This allows us to dynamically adjust the impact of class labels, resulting in more varied and higher quality outputs. We conducted experiments on the ImageNet 1K benchmark to assess the design, performance, scalability, and efficiency of our AIM model. We provide AIM in 4 different scales, with detailed configurations available in a table. Unless noted otherwise, all models in the following sections follow the same setup as outlined in the table. Our image tokenizer is set with a downsampling factor of 16 and initialized with pre-trained weights from Llama Gen. For training, we used class-conditional AIM models on the ImageNet 1K dataset at a resolution of 256 by 256 pixels, utilizing 80 GB A100 GPS. Each image was divided into 256 tokens. We employed the AtomW optimizer with specific beta values and a weight decay rate. The learning rate was set to 100,000th per batch size of 256, with training epochs ranging from 300 to 350 based on the model scale. We applied a dropout rate of 0.1 to the class embeddings to support classifier-free guidance. For evaluation, we primarily used the Frechet inception distance, FID, and also considered the inception score, IS, precision, and recall as secondary metrics. Our baseline results were sourced from the original paper for accurate comparison. We examined the scalability of AIM by adjusting model parameters and training compute, measuring image quality with FID. Our findings show that FID decreases with more training steps across all models. A strong negative correlation between FID and model parameters indicates that larger models significantly enhance image quality. These results confirm AIM's scalability, showing that increasing model size and training duration improves image quality, highlighting the importance of investing in these areas for better performance. Due to the limitations of ImageNet 1K, we did not scale the model size beyond 2 billion parameters. We compared our models with various existing generative methods, including GANs, diffusion models, masked generative models, and transformer-based autoregressive models. Our aim achieved state-of-the-art performance among autoregressive models and showed competitive results against diffusion models. Lastly, we evaluated the impact of ADALN and ADALN single on model parameters and performance across two scales. As the hidden size increased, the growth in parameters from ADALN showed a nonlinear relationship with performance improvements, indicating redundancy. This finding emphasizes the need to balance parameter count and performance, leading us to explore ADALN group. We further analyzed how the number of groups in ADALN group affects parameter count and performance, finding that with 4 groups, ADALN group performs comparably or better than ADALN across scales, confirming that excessive parameters in ADALN can complicate training without significant benefits. Section Summary. In this section, we describe our approach to class conditional image generation using autoregressive models, where we embed class labels to predict the next token in a sequence while minimizing prediction loss. We also implement classifier-free guidance to enhance output quality and demonstrate the scalability and performance of our AIM model through experiments on the ImageNet 1K benchmark, achieving state-of-the-art results compared to other generative methods. Section: Effect of architectural enhancements. In this section, we validate the effectiveness of our enhanced method by performing an ablation study on the AIM-L model, where we added various components. We found that the CFG, with a default factor of 2, has a strong influence on the FID score. Although the PE component has a minor effect on FID, it significantly enhances visual perception. Additionally, incorporating ADALN also notably impacts FID. For more detailed experimental results, we refer to the appendix. Regarding inference efficiency, we compared the inference speed of the AIM model with other models, as illustrated in the figure. Our AIM model shows a clear advantage in speed. The transformer-based models benefit from acceleration through flash attention and KV cache, but this is only applicable to autoregressive models. More detailed results can also be found in the appendix.